Welcome to Vector Calculus, Divergence and Coil. Using the del operator on a vector field. We can also use the del operator on a function, a scalar function, and we would call that the gradient. That would be on a separate video because we're concentrating on the vector field right now. The del operator in Cartesian space is represented by the symbol upside down triangle and is defined as the partial respect to with respect to x in the unit vector of the x, the partial respect to y in the unit vector of the y, and the partial respect to z, the unit vector in the z direction. While the del operator is not strictly a vector, it is partial derivatives for a vector, each partial multiplied by the corresponding unit vector. When the del operator is applied to a vector using the dot product, a scalar results. We would take each product, partial times what an x1, and sum those. This is called the divergence of a vector field. In an infinitesimal volume around a point, if the field strength is decreasing, the divergence is positive. As an example, if a mass is decreasing, such as by sublimation, that would be for a solid, the sort of equivalent of evaporation. And yes, solids do disappear. We call it sublimation. The gravitational field due to the mass has a positive divergence because the mass is getting less, gravity is getting less. But if the mass is increasing, such as a planet capturing meteorites, the divergence of the gravitational field is negative because the mass increases, gravitational field increases, its divergence decreases. So let's take an example. Find the divergence of the vector vxyz equal 2xy plus 3z squared xy xz cubed. Yeah, your three components. So we're going to take the partial with respect to x and dot it with the x component here. And so the partial with respect to x operating on 2xy plus 3z squared, everything being held as a constant except the x, would give me 2y plus 0. So I end up with 2y partial with respect to x being 1. So I end up with 2y. Partial with respect to y, operating on the y component here, is going to give me x. And the partial with respect to z, operating on the z component, is going to give me 3x z squared. So this would be my divergence. It will be a scalar, and it will represent how fast the field is changing. And you can see in the various variables. Another example, find the divergence of vxyz equal 2y xz 3xy squared. So we can take the partial with respect to x of 2y. That's going to give me 0. The partial with respect to y of xz is going to give me 0. And the partial with respect to z of 3xy cubed is going to give me 0. So adding 3 zeros, I get 0. So here the field is neither, it's not has no divergence. It is steady. When the del operator is applied to a vector using the cross product, a vector results. This is called the curl of the vector field. In an infinitesimal volume around a point, the curl gives the axis, magnitude, and direction of rotation of the field. Okay, so we're going to take the cross product of the del operator with a vector. And the way we do that is with permanent. So we need three coordinates. So we take the three unit vectors, I, J, and K, representing the unit vectors in the X, Y, and Z directions. Then we put the second row as the three partials operating. And in the third row, we put the components of the vector, the X, Vy, Vz. Well, we take, here what we're going to do is expand by minus. And I can tell you from having taught for many years, I had a lot of students, they wanted to do everything on their calculator. And yes, your calculator does solve 3 by 3 determinants, but not when a row is unit vectors and another row is operators or partial derivatives. Here you have to know the technique. Now, there's a shortcut that people use going with positive and negative diagonals, and when they get off the end and wrap around, the students often have a lot of trouble with that. It's best to just go ahead and deal with expansion by minus. Expansion by minus means I take the top left position, I, and then I make a 2 by 2 determinant with what's left, partial respect to Y, partial respect to Z, V, Y, V, Z. Then we alternate signs, so we have a negative, a J from here, and then we don't use this column, but we use this column and this column. So it'll be partial respect to X, partial respect to Z, Vx, Vz. Then we take the K, the unit vector, and we don't use this column, so we take these four to make this matrix, the determinant. Partial respect to X, partial respect to Y, Vx, Vy. Now, to evaluate a 2 by 2, you go down the diagonal and then you go in the reverse diagonal and subtract what you get. So we're going to do partial respect to Y, Vz, minus partial respect to Z, Vy, all multiplied by the I unit vector, minus. Now we're going to go partial respect to X, Vz, minus partial respect to Z, Vx, plus, signs alternate, partial respect to X, Vy, minus partial respect to Y, Vx. Okay, and if I had a 4 by 4, now I'm not going to have that here, but if I had a 4 by 4, I would have to deal with reducing to 3 by 3s with an expansion by minus, and then reducing to a group of 2 by 2 determinants, and so on. This technique is stable. Now, an example, find the divergence and the curl of a vector Vxyz equals 3x, y, 2x, y squared xyz. So let's start with the divergence. It's the dot product. So we're going to take the partial with respect to x of 3xy, and that's going to give me 3y. We're taking with respect to x. We treat the y as a constant, so we got 3y. The partial with respect to y of 2xy squared is going to be 2x, and this is going to give me 2y, so it's going to be 4xy. And the partial with respect to z of xyz is just going to be xy. Now these can be grouped, so we're going to end up with 3y plus 5xy. Now, this is not a vector. Now, we started with a vector, but we came out with scale. So this is the divergence. For the curl, partial derivatives are going to be needed. Again, we're going to be using the del operator. But this time we can do the cross products. So we're going to, and I just went ahead and didn't start with the 3x3 because I had just done that in the video, and you can go back and see. But this is the line after it's been expanded by minus. And so we're going to get the partial with respect to z. Let's see. Sorry. The partial with respect to y of vz is going to be xz, and the partial with respect to z of vy is going to give me the 0 minus this one. I'm going to have the partial with respect to x of vz. That's going to be minus x minus yz, and the partial with respect to x with respect to z of vx is going to give me 0. Partial with respect to x of vy is going to give me 2y squared, and the partial with respect to y of vx is going to give me negative 3x. So I'm going to get a nice little vector, and you don't have to write the zeros. I do that when I'm presenting something so people can follow. I often will write a plus 0 just so people know what goes there, whether or not anything shows up in this particular problem. In reality, you don't have to do that. Another example, find a divergence of v xyz equals yz xe xy. So if I take del dotted with yz xe xy, the partial with respect to x of yz is 0. The partial with respect to y of xz is 0. And the partial with respect to z of xy is 0. I end up with 0. In this case, the field strength is steady. It's not increasing or decreasing. So that is a possibility. And that's another thing I keep telling students. 0 is a good number. It sometimes happens. So this example, we're going to find the curl of the xyz equals xyz. For the curl, we want del cross the vector xyz. So we're going to have, and again, I didn't show you the 3x3 determinant, but only the final step after the expansion. So if you need to go back, it's going to look identical after this step. So we're going to want the partial with respect to y of Vz, and that will be 0. And the partial minus the partial with respect to y, with respect to z of Vy, that's 0. We have the minus sign, and the minus sign will partial with respect to x of Vz is 0. And then we get the negative from here. So the two negatives make the positive one here. The partial with respect to x with respect to z of Vx is 0. And then we get the partial with respect to x of Vy is 0. Minus the partial with respect to y of Vx is 0, or 0, 0, 0. So this field is not rotating. Well, sometimes having to give these special cases of a non-rotating field and so on are important that students see them. They are possible, and I like to give a thorough presentation. I hope you enjoyed it, and I would appreciate it if you would hit the subscribe button, because we have many videos, and if you needed this one, there's a good chance you would need some of the others. Some are practice problems and some are theory. I'd like to start with the theory and then add practice problems later if they are needed. And if you need a special topic, I don't mind if you leave a comment and say, hey, can you provide a video of this or of that? It's best if it's something people need. Thank you.